Welcome everybody. It's a real pleasure to have Jason Lee here with us today. So Jason is assistant professor at in the Department of Electrical Engineering at Princeton University, where he is part of theoretical machine learning group. Before that, he was at USC as faculty for 3 years, I believe. And before that, he was a postdoc working with Michael Jordan at Berkeley. So he does lots of wonderful things, and I guess today he is going to talk about foundations of deep learning, and it sounded super cool. So it sounded so cool that I decided not to take vacation today and actually come listen to his talk. This was the main motivation for not taking vacation today. So it's really exciting, and we spoke briefly before, so I think he's willing to take questions during the talk. So you can raise your hands, and we'll try to monitor. And if there's sort of longer discussion things, we might want to say that till the end as well. Okay, thanks a lot, and welcome.
All right, thanks for having me. So I'm going to talk today about some theoretical work on the foundations of deep learning. Just some quick motivation. Deep learning has been very successful. I'm going to go very fast. I think we all know this. Throughout all the applications of AI, many of them are driven by deep networks. How do I turn off this thing that keeps telling me to admit people? Because it keeps popping up. Okay, I'll just ignore it. Okay, yeah. So today's talk won't be about these applications, although very much motivated by them. I'm going to talk today about towards developing some theoretical understanding of the optimization and statistical or generalization aspects of deep learning. First, let me tell you why it's not obvious or what's difficult about it. We have 30 years of both work in statistical theory and optimization theory. Why don't these already directly solve deep learning? And then I'll tell you about some specific lines of work based on linearization, the neural tangent kernel, and how to move beyond that approach. Okay, so roughly speaking, the challenges of deep learning can be summarized in two parts. The first one is just the optimization landscape is non-convex. There's a lot of critical points. There's a lot of bad local minima, and we don't really know much about it. So there's sort of no black box approach that you can sort of expect that to say that SGD will work because it's not convex. So there's no ways to sort of abstract away the difficulties here. The second one is that the generalization of deep learning is very different from traditional statistical models. Deep networks are large. They have more parameters than samples. They're heavily overparameterized, nor do they have any explicit sort of regularization promoting structure, such as like say sparsity, which also has more parameters than samples, but essentially the regularizer makes it implicitly low dimensional. And deep learning, at least on the surface, does not have any structure like that. Even worse is these two things are sort of very coupled together. The choice of optimization algorithm will affect your statistical performance. For example, I can find a global minimum that completely doesn't generalize, or I can use SGD and find one that generalizes a lot better. And a lot of the things that we use to improve statistical performance, is unclear what they do to the optimization. For example, regularization, dropout, batch norm. The effect of all of these things on the optimization landscape is pretty unclear. And of course, they're intertwined. You can't really take it apart. Contrast this to convex optimization, where let's say I'm solving logistic regression. It doesn't matter how you learn a logistic regression model. You can use Newton's method or stochastic gradient descent. As long as they get optimization error epsilon, and then I can bound the statistical error independently of the algorithm, right? Because the global minimum is unique. Regardless of which algorithm you use, you converge to the same thing. And that's very much not the case in deep learning. The choice of algorithm, even the choice of random seeds, the order in which the data is read, all of these affect the quality and the precise minimizer or precise point you reach at the end of your algorithm. Okay, so let me first start talking about some work we did a while ago towards understanding sort of what is the best black box kind of guarantee you can expect of a local search algorithm such as gradient descent or stochastic gradient descent. So roughly speaking, we've showed a few years ago, as long as you initialize randomly, you won't get stuck at saddle points. You'll avoid saddle points and converge at least to a local minimizer. Here it says strict saddle, but a strict saddle is essentially strict saddle property means that every saddle point has some negative descent, so it's not degenerate. And this is true for almost all optimization algorithms except Newton's method. All of these algorithms will converge to local minimizers. Why is this important or interesting at all is that this sort of lets you isolate how to analyze a lot of optimization landscapes for a fairly large number of problems that are non-convex, but SGD will find the global minimizer, such as essentially all of these problems are some form of matrix factorization or tensor factorization in some shape or form. For example, shallow neural networks, matrix completion. These are all non-convex problems but however, running SGD will give you a good answer. They're non-convex, but SGD provably finds a solution of high statistical quality. Okay, so this is not the case in deep learning in that, but however, you have a lot of flexibility. You can try to design a loss function by changing the architecture usually, so that SGD will succeed. So on the left, I have a function that's bad. SGD won't do anything good. On the right, there's a function that and where SGD will succeed. It won't ever get trapped in a bad point. Let me show you this with a small toy experiment. On the left-hand side, I generated data from a neural network with 50 neurons. So there's one hidden layer. The hidden layer has 50 neurons, and then I do SGD on this model, and the model is the same as the teacher network. It's also 50 neurons, and I ran SGD 5 times. Every single time it converged to a suboptimal solution. You can see none of these curves go to 0. They go to something like 0.13 and then around 0.17. So in fact, they find different local minimum all times, and none of them have the same objective value. So, and none of them are global min. The global min here is 0. So it's easy to certify. On the right-hand side, I changed the landscape. What I did is I made a model with 100 neurons. The data still comes from a model with 50 neurons, and then I changed my architecture, the one I'm fitting, to have 100 neurons. So now it's sort of misspecified. However, so this misspecification, if you're a statistician, makes no sense. I know my model had 50 neurons, so I should fit the one with 50 neurons because it's statistically efficient. Anything else would be wasteful. So I fit this model with 100 neurons, but something surprising happens is that every single time SGD finds a global minimizer now. Okay, so so what this says is that you can sort of design a good loss landscape simply by over-parametrizing and using a bigger network. This is, of course, well known in practice. I don't know who first discovered this, but in the theory community, Livni and Shamir first pointed this out. Okay, so let's try to see what over-parametrization can buy us. So basically, the conventional wisdom here is that if you're not getting solutions of at least low training error, then you should increase your model size until the training error is near 0. So of course, there's some theoretical questions here. Is how many parameters, how large of a network do we need to fit this data? And are we worried about overfitting? If we add too many parameters, at least it seems we have the potential to greatly overfit. Okay. So you can sort of do some unrigorous physics-ish calculations, and it kind of suggests that the number of parameters you need at least is some constant larger than 1 times the sample size n. This is at least what is the minimum needed in a sense. But what can we show? What we can show is that if you run gradient descent from a random initialization, and if you have a network, a ResNet or a feed-forward net or a CompNet, it doesn't really matter, and the width is some polynomial in n and the depth, then you converge to a global minimizer with 0 training loss. This theorem is very pessimistic. It says it needs something quite wide. It needs something at least linear in n, but probably polynomial in n. But it's very general theorem. It holds for almost any architecture, any activation. You can use SGD or any reasonable descent algorithm, any loss function, hinge, logistics, so forth. And it says, so it's very surprising, your loss function is non-convex, but almost any algorithm from a random initialization will converge to a training loss of 0. And of course, in non-convex optimization, we should not expect this. So what's happening? So if you think hard about this a little bit, it's actually not surprising at all. Let me illustrate to you what's happening. So let's first consider just doing a Taylor series on our neural net architecture. F sub W is our network with parameters W on input X, so returns a scalar. We just do a Taylor expansion and drop all the higher order terms, and I'll in fact also drop the 0th order term. What remains now, I'll denote F1 of X, which is a linear function in W. Okay, so it's a gradient of F at W0, dot product W. So it's linear in W. And so this is what was pointed out in these references. In the region around W0, neural nets will behave like a linear model. In fact, this is true for any smooth function, is that locally they're linear, nothing special in neural nets. Okay. So the idea now is try to replace the nonlinear function fw with its linearization. And then, so you have some convex loss function, let's say logistic loss or square loss. The loss function is convex in F but not convex in W. But now I replace fw with a linear function of W. So it was W transpose gradient fw. And now this is linear on W, right? Because if you compose a convex loss function with a linear function of W, it's convex in W. And by Taylor's theorem, the gradients also approximately agree here. Okay, so what this says is that gradient descent on this nonlinear neural net is approximately gradient descent on a linear model. As long as I stay close to initialization, you can make all this formal. The training error now converges to 0 at a geometric rate, since the linear model is essentially strongly convex. And you can carefully bound this approximation error from throwing away the Hessian term. Remember, I threw away the 2nd order term in my Taylor series. Okay, so all of this can be made rigorous. Okay, so roughly speaking, the intuition is that what gradient descent is doing actually is it's just solving this linear equation. You have a Jacobian matrix, which is you stack all the gradients of the data points, the gradient with respect to the parameters, but applied to the data points. That's this big matrix times the vectorization of your parameters equals to the label y. Because you're overparametrized, this matrix, Jacobian matrix, is full rank, and there is a solution. And gradient descent on a linear model, it's well known that it finds a solution closest to initialization. This is a property of using gradient descent. And you also need to check that the thing you converge to is close enough to initialization, so the Taylor approximation is faithful. And you can do all these and to get a rigorous proof. I won't do that, but let me just explain to you now what you're actually learning if you follow this approach. So if we ignore everything except the linear term in the neural net, what you arrive at is a kernel method. Remember, every single linear model, it corresponds to some kernel. The kernel in this case is given by the inner product of the gradients at 2 data points. You have a data point x and a data point y, and then you look at the gradient of the neural net at initialization and their inner product. That induces a positive definite kernel, call it K. And what these papers show is that when gradient descent, if M is large enough, the overparametrization is enough, you learn the same predictor as a kernel method with this particular kernel known as the NTK or neurotangent kernel. So this is, of course, this is kind of good news if you're a theorist, because we know a lot about kernel methods, and we know how to understand the sample complexity of kernel methods. For example, every kernel corresponds to a space known as the reproducing kernel Hilbert space, or an RKHS, induced by the kernel. This is given by Mercer's Moore-Aranjan theorem. And then the sample complexity of such a kernel method is given by the RKHS norm of the target function you want to learn. This norm squared divided by the desired accuracy squared. So in a sense, this gives you a quite complete understanding of what gradient descent does on very, very wide networks, is that this is a sample complexity and the training error goes to 0 linearly. And this is the number of samples you need to get epsilon generalization error. So that's sort of the good news. However, it's a double-edged sword. We know a lot about kernel methods, so we also know their limitations. I won't go into much detail here, except to say that essentially these kernel methods will not, these neurotangent kernels perform exactly the same theoretically as a polynomial kernel. So for example, let me just look at the second bullet point, is that if you have any less than n less than d to the L+1 samples, you can only do as well as a degree L kernel. The sample complexity of a degree L+1 kernel is d to the L+1. So if you have any less than that, you can only do as well as a kernel of 1 lesser degree. And all of these examples basically show that, or all of these are theoretical lower bounds showing that if you train a wide, very overparameterized neural net with gradient descent with a small learning rate, you cannot do better than a polynomial kernel. So these are negative, provable negative results. And they all have the same spirit. What's happening is that when you use a kernel method, especially the neurotangent kernel, it's sort of rotationally invariant, at least for a fully connected network. And then so you cannot, if you're to learn one direction, you have to learn some other direction. And so basically you can, what boils down to is learning polynomials of a certain degree, and you clearly need dimension to the degree power to learn a polynomial. Okay, so that's sort of the bad news, is that we went through all this pain of understanding neural nets, and then theoretically, the answer we got is that they're no better than polynomial kernels. And of course, this does not, this is not consistent with our empirical observations. Let me illustrate a little bit the intuition of these lower bounds, the negative results. So all of these negative results essentially rely on functions where the signal is localized on a small number of directions. The simplest case of this is to look at this sort of what I'll call rank 1 polynomial, beta transpose x squared. So this is a quadratic monomial. It's degree 2, but it's very special. The only direction that matters is beta. If you run a kernel method that's rotationally invariant, it's essentially going to learn, it's going to implicitly do a lifting. It's going to lift x to xx transpose, and then it'll learn a d by d matrix, so that's d squared parameters, w star. But it cannot enforce the low rank structure on w star. So the sample complexity will be, roughly speaking, d squared over epsilon squared. So when you use a kernel method such as NTK, you throw away the low rank structure of the polynomial. However, the minimax sample complexity to learn this function f star is clearly d. I just need to learn beta, which is d parameters. So sort of, if you look at kernel methods or the NTK, you throw away this low rank structure and you lose a factor of d in your sample complexity. you can generalize this arbitrarily. Let's say I look at general low rank polynomials of rank R of degree P. The correct sample complexity here is dr, roughly speaking, is you just need to learn all of the directions beta that matter, and then you've learned the function f star. If you run a kernel method, your sample complexity will be very terrible. It'll be d to the power of p, so exponentially worse in the degree. Because essentially you're going to just learn all degree p polynomials in dimension d. There's no way to, you have no inductive bias in any kernel method that can impose this sort of low rank structure. There's some results that can do this algorithmically, but in general, sort of this minimax sample complexity of dr is not attainable, or we don't know how to attain it. But we can get this in certain special cases, such as when the degree is all 2. And we have some papers on doing that. Okay, and there's a different line of work that suggests that SGD has good inductive bias. So all of these results sort of say that SGD will learn some sort of simple low dimensional functions. So for example, on 2-layer networks, this result of Rosette and Bengio, they show that it's equivalent to sparsity on the space of neurons. So they show that just by doing weight decay, this induces an L1 norm on the space of neurons. So you sort of select a set of neurons or features that are sparse. And also, even just on simple, boring linear networks, you can prove that SGD finds solutions that are low-dimensional solutions. A linear network is, of course, just a linear function, so it's just a linear mapping. But SGD will tend to find solutions where the linear mapping has decaying singular values, so in some sense, low-dimensional. And same thing with dropout on linear networks and leads to low-rank factorization. So all of these results, none of these are fully rigorous, but all of them are sort of physicsy in style, and they sort of suggest that SGD can do something interesting. It can learn low-dimensional representations. So what is going on in all of these sort of non-rigorous or not fully rigorous results is what's happening is sort of the opposite of the neural tangent kernel regime, is you're moving substantially from your random initialization and you're attaining regularization or max margin with respect to some norm. And the norm is not this close to initialization. So basically you need to forget where you initialize is sort of the theme of all of these results. Okay, so let me tell you how to do this now in a provable and rigorous fashion. So the rest of the talk is how to design algorithms that can computationally efficiently also utilize more of the parameter space than sort of this linearization regime. The approach is very simple. The approach will just be use higher order Taylor series. Okay, so remember in the neural tangent kernel regime is that we started off with only keeping the first order Taylor's theorem. Now I'm going to keep the second order, and for now I'll throw away the higher order terms. I'll talk about at the very end how these higher order terms can also help. So here in a 2-layer network, I'll call the term from the linear part of the Taylor expansion, I'll call it F1, and I'll call F2 the quadratic term. So in particular, just remember that F1 is linear in W, F2 is quadratic in W, and we're going to try to move W further, so F2 will start mattering. Okay, so immediately you notice that there's some bad news. You can do some heuristic calculations. If you want to do something different than the linearization, you want F2 to be much bigger than F1. But in fact, this cannot happen is when you're very, very overparameterized. And then F1 is actually much bigger than F2. And there's already a global minimum near the initialization. So So what will happen is that gradient descent will just go to the closest global minimizer, roughly speaking. And it's never going to see the rest of parameter space where you could have moved further. And there are these global minimum far from your random initialization with, they have the same training error. They all have training error 0, but perhaps they have much better test error. But you can never go there because there's already a global minimizer next to you, and you kind of just find the one that's close to you. Okay, so there's several options now that about how to sort of escape this local region, and this local region has some global minimizers, so escaping it is non-trivial. You do need to modify your algorithm in some way. The first candidate to doing this is to inject a large amount of noise, or use SGD with a sufficiently large learning rate so it comes with a large amount of noise. If you add enough noise, what will happen is that F1 effectively cannot learn. Is your neural tangent kernel will degenerate to a linear kernel, so it can only learn linear functions. And it cannot learn anything except a linear function, and thus it must move a large amount away from initialization. The second approach is to add regularization, such as weight decay. And then if you add weight decay, then the global minimizer won't be near your random initialization. Or you can look at the case when the networks are not super overparameterized. They have some finite size width M. And then it's possible that there's no global minimum near your initialization. Or you can try training for a long time with a logistic loss or exponential loss instead of square loss. And then eventually you have to leave, although it takes very long time. It turns out that these are all potentially viable strategies, but difficult to execute. The one that's simplest to look at is number 1, adding noise so that the linearization effectively cannot learn, which is what we'll do. Our simple observation is building on a paper by Alan Zhu, Yuanzi Li, and Yingyu Liang. It's observing that F2 sometimes can be the dominant term. So consider a parameter change that's multiplied by a random matrix of plus minus ones. So the movement is now W multiplied on the right by D. So the you're multiplying the by plus minus ones. So what happens now is the linear term has cancellation. The linear term F1, remember, is linear in W. So when you multiply the linear term by plus minus ones and sum them, there's some cancellation of square root M. So it'll be square root M times smaller than its absolute value, essentially. So the randomness gets cancellation, but on the quadratic term, there's no cancellation because it's quadratic. You square a plus minus 1, it's 1, and there can be no cancellation. So for special weights, you're always going to get this cancellation, and the linear term will not be able to memorize the labels Y. Okay. So effectively, what's happening is that you can now have a quadratic term F2 that outputs things of size order 1, which is our goal. The label is order 1. So to fit the labels, you need to output order 1. And the linear term is very small, so it cannot learn, or it's not contributing to learning. So namely, if you move a region M to the minus 0.25, then this will happen, is that the linear term will be output something little O of 1. This quadratic term output something big O of 1. So at least you have the potential of not using the linear term. Okay, so algorithmically, how do you do this? So we're going to modify the algorithm. We're going to force SGD to learn neural nets where the linear term F1 does not matter by every time drawing a random data point and then drawing a random diagonal matrix. And then the random diagonal matrix will multiply the parameter W. So when we take the gradient, we're always going to learn weights where essentially they're like modulated by these plus minus one, so they get this cancellation. And then we'll introduce a weight decay as a regularization, just to control how far it moves. Okay. So this is our new algorithm. It's SGD, but every time you draw a random data point and a random diagonal matrix. Okay. So I'm going to talk about next 3 theoretical aspects of this new algorithm. So the first one is essentially about computation. So can you still find global minimizers in a certain region? Like essentially, can you fit, will the training error go to near 0? The second question is, what is the expressiveness of the model? Can I approximate arbitrary functions still? And the third one is, what is the sample complexity? For the linearization NTK, all of these are answered, and they're all answered in a satisfactory manner, except the last one. The sample complexity of NTK is potentially terrible. It's basically doing polynomial regression. So basically, we would like something where, yes, you can find global minimizers, it's universally expressive, and the sample complexity is better than just doing polynomial regression. Okay. The theoretical tool for studying this is very similar to what we did before. Is again, we're going to introduce a coupling or approximation. Instead of considering a general nonlinear network, I will replace it with this F2, which is the quadratic approximation to the neural network. And then we'll be able to prove that when you're sufficiently overparameterized, namely when M is large enough, the gradient of my approximation and the Hessian of my approximation are close. So essentially what that means is I can study all the aspects of my loss function by plugging in this quadratic function of the parameters instead of a neural network, which is nonlinear. So I've replaced nonlinear with quadratic function. The model is quadratic, so the loss function is not quadratic. The loss function, if it were square loss, for example, would be quartic polynomial. Okay. But at least you know, studying a quartic polynomial is somewhat easier than studying a nonlinear neural net, and so it is still a little bit simpler. Of course, when you're optimizing quartic polynomials, they're no longer convex. Note that when I replace the loss function with linear, it just becomes convex, right? And convex optimization is easy. I run any algorithm, basically, I'll get the global min. Here, it's very much not the case. Even locally, this function is non-convex, and it's not locally convex, unlike the neural tangent kernel approach, and because it's over a much larger region. In neural tangent kernel, instead of m to the minus 0.25, you're moving m to the minus 0.5. So basically, you're moving 1 over root m instead of 1 over m to 1/4. So this is a larger region, and in the larger region, it's not convex anymore. It is still the case that every local minimizer is within an epsilon of being global minimizer. So what we'll do is we'll use SGD, we'll run SGD, and SGD is known to find local minimizers, and in this restricted region, all the local minimizers are in fact global. So that's how we'll deal with optimization, is we'll be able to find global minimizers within this region of m to the minus 1/4, which is 1 order larger than sort of what before the linearization method was doing. Now let's look at expressiveness. The expressiveness is not very interesting. It's essentially, you're going to be able to express any function that can be written in this following integral form. And then for most activations, this is essentially all even functions, all functions that are even. And you can get back the odd functions just by introducing like a bias term. I won't talk about that, but essentially it's more or less the same as NTK, is you can approximate any arbitrary polynomial function, and polynomials are universal, so it implies universality. So essentially you don't lose any expressiveness by using this quadratic model instead of the linear model. This is not surprising at all. It's essentially just a different random feature model. Okay, so let's look more carefully at this model we're using to approximate the neural network. It looks like this. It's a sum of terms of the form outer product of W transpose times the second derivative of activation times XX transpose. Okay, so you might be looking at this and thinking it actually looks a lot like a linear model. You can try to write F2 of X as theta inner product some psi. And then it looks sort of like a linear model with the following feature map given by psi. So this is sort of a, I'll call this a feature map. It doesn't depend on the parameter. And so the model is linear in this feature map. It's theta times the feature map. However, the parameter theta is a quadratic function now of the W's. And that's the only distinction. If you look at the function f1, it was linear in theta, but theta is W here. And so f1 is linear in the parameter W, and f2 is quadratic in the parameter W. Although in a lifted space, you can think of f2 as linear. Okay. So you might be thinking that both methods seem like linear classifiers in some infinite dimensional feature space, which is true. But actually, one of them is a kernel method. The linearization is a kernel method, and the second method using the quadratic lifting is not a kernel method. So how is this different from a kernel method? Let's look at the inductive biases. Okay, let's assume for now that I just use weight decay, the L2 norm squared of all my weights, and I constrain them to be less than B squared. And here I'm upper bounding the Rademacher complexity of this method. Exactly what is the Rademacher complexity is not very important. It's just something that upper bounds the generalization pair. But what happens here is that when I upper bound the Rademacher complexity, I'm going to use a nuclear norm on the sums of the outer products of the W's. And so the dual to that by Holder inequality is the operator norm. So what I get is, and the nuclear norm of the sum of these W transpose is actually, in fact, just the Frobenius norms of the W's, which exactly corresponds to my weight decay or Frobenius norm regularization. So essentially, but this is a very different inductive bias than what an RKHS method would get. An RKHS or kernel method can only ever get L2 norm inductive biases. So it can never get a nuclear norm, which is essentially a Banach space instead of a Hilbert space. And so when do you gain here? So you can compare the Rademacher complexity of the quadratic method versus the linear method. For example, consider data where the second moment matrix, the covariance matrix, has condition number order 1. So for example, basically saying that it's not too skewed in any one direction. It's sort of whitened. Then the operator norm of this random feature covariance matrix will be order 1. You can calculate this using like matrix Bernstein or something. But the kernel matrix, if you look at the kernel method's Rademacher complexity, it's bigger by a factor of D because it depends on the Frobenius norm of these random features rather than the operator. So essentially what's happening is that in the generalization error, you're gaining a factor of D. When the data covariance is not too skewed, when the data matrix has covariance operator norm bounded, then this quadratic parametrization, although both are universal approximators, induces a better inductive bias. Okay. So let's look at some examples of this. So whenever your covariance matrix is bounded, for example, one of the lower bounds I glossed over in the beginning was a very simple function. It was the function x1 times x2. So the goal is to learn XOR on 2 coordinates. The rest of the coordinate, there's D coordinates in total. You're trying to learn the XOR function, which basically x1 times x2. The rest of the D minus 2 coordinates are all noise coordinates. They have no signal on them. What we proved is that every single kernel method, including NTK, needs d-squared samples. Any rotationally invariant kernel will need d-squared samples. It has no way to distinguish x1 times x2 from like x5 times x203. So basically, you have to learn all pairs xi times xj to learn this function if you're using a kernel method. And that requires seeing d-squared samples to learn everything of the form xi times xj. There's just d choose 2 of them, and so it's easy to show you need, there's a lower bound that you need d-squared samples. The quadratic model will do this with d samples, which is the optimum here. To learn x1 times x2, you need at least d samples. And that method gives you a statistically and computationally efficient method. It proves that SGD on a 2-layer network will learn it with d samples. Similarly, you can look at functions of the form theta. Theta is now a constant rank tensor, so order k tensor. So it's basically a homogeneous polynomial of degree k, of low rank. So x Kronecker product k times dot multiplied by this multilinear form theta. Montanari and Gorbani and Aurora and several other authors show that you need d to the k samples. So namely, there's a lower bound showing you need at least d to the k samples, and there's an upper bound showing you with order d to the k samples you can learn. The method I talked about here gives you a modest improvement. You can do it with d to the k minus 1 samples. So you shave off a factor of d. So we're still very, very far from the minimax optimal sample complexity. The optimal sample complexity here is d. The naive method of using linearization will get you d to the k. The method I just talked about will get you d to the k minus 1. You can also look at very concrete problems like matrix completion. So low rank matrix completion is this, it's usually done by nuclear norm minimization. You can look at what a neural net in the NTK regime would do, and it does something very, very similar. A neural net in the NTK regime, in fact, needs to see every single sample to, before it can get 0 error, 0 or near 0 test error. So roughly speaking, if you want to get test error less than a constant 0.1, you need to observe d-squared samples. This is terrible because there's only d times r, there's only order dr degrees of freedom, and the matrix is d by d. So if you see all of them, you know, this is like, you're basically not learning, you're just memorizing. The optimal sample complexity here is dr. The method I just told you about gets something around dr squared samples. So it's essentially optimal. The d is often the rank factors, but that's generally not so important. Okay, okay. So what I told you about was basically how to move a small away amount from the neural tangent kernel. Essentially, we were moving the parameters from 1 over root m to 1 over m to a quarter. So you might be wondering, what if I want to use more of parameter space? What if I want to move, you know, order 1 away? How do I think about this? So of course you can, the obvious thing to try is to just expand this in higher order Taylor series. Is you can just collect the terms. You have the first order Taylor expansion, that's f1, f2 is the second order term, so it's a quadratic in W. The cubic term is f3 is cubic in W, and so forth. Now you can start, as you move further in parameter space as a function of m. So for example, if you move m to the minus 1 over 2k away, then you can truncate this Taylor series at the kth term. So just as an example, if I move m to the minus 1/6, then I only need to look at the first 3 terms. So basically, if I move, and of course, if I move order 1, which is all of parameter space, I need to keep all the terms of the Taylor theorem. So basically what I can do now is if I move a certain distance from initialization, I know how to couple a neural net's optimization trajectory to that of using this FK, which is the truncation of the model at the kth order. I won't go into details here, but sort of the expressivity is the same as before. It's essentially still a universal approximator as long as you use something like a ReLU as the activation or a sigmoid. As long as your activation is analytic and non-polynomial, you have the same expressivity, but you can gain more in the sample complexity. So now we need stronger assumptions on the data. So we're going to assume that the kth order moment tensor of the data. So before I was making assumptions about the covariance of the data being well conditioned. Now I will require that the kth moment of the data is well conditioned, is O of 1. Then we can learn any low rank polynomial with d to the p minus k plus 1 samples. So essentially, the higher the order I go, meaning the more of parameter space I use, I get a larger improvement over the linearization. I improve by a factor d to the k minus 1. And of course, the optimal thing here to do is to have k equal p, and then you can learn with order d samples, a low rank polynomial. But we don't know how to optimize for very high order k. So as you can imagine, when the k was 1, that's exactly linearization. And then there was a convex model, and optimization was completely trivial, essentially. It reduces to convex optimization, which we can leverage all the theory for that. When k is 2, I already had a non-convex model, but luckily, it was a non-convex model, but the local minima all had some good properties. All the local minima were global. So although it was non-convex, I could use SGD, and SGD would never get trapped in bad places. And then I could prove SGD would find solutions of low training error. As soon as k is 3, it's possible already that there's bad local minima, potentially high order saddle points. We don't really know how to deal with this yet to optimize very high order. And of course, we know that it should not be possible theoretically either, because when the order is high enough, you have the full expressiveness of any deep network. And there's many negative results about learning deep networks. It implies you can learn parity and so forth, things that should be hard. The current best thing we can do is d to the power of p over 2, where p is the degree of the polynomial. What that means is I have a polynomial that's, let's say, rank 1 or constant rank of degree p. If you use a kernel method, you need d to the p samples to learn this. We have an algorithm that's computationally efficient using SGD on a 3-layer network that can do this with d to the p over 2 samples, but still very far off from the optimal of d samples. So there's still a considerable statistical and computational gap here that we don't know how to close yet. Okay, so let me quickly finish. Sort of this neural tangent kernel way of thinking is very powerful, but it greatly restricts the sort of statistical power of the model. Essentially, it makes optimization easy, but makes the statistics not so great. Essentially, you can only just learn polynomials like a kernel method. By looking at higher order NTK, it gives you a systematic way to use a larger region of the parameter space. By using the larger region of the parameter space, you preserve the expressiveness, but you can immediately get better inductive bias, and thus you learn with fewer samples. The high level point here is that when you're over-parameterized, there's global minimum of the training loss everywhere. In particular, there's ones near random initialization. There's also ones far off from random initialization. But the ones near random initialization are not the ones we want to find. These have very crappy inductive bias. They essentially just learn polynomials. By utilizing more of the parameter space, we can sort of learn these more structured or low rank polynomials, which includes at least some problems that theorists have looked at, such as matrix completion, tensor completion, things like that. And that's all I have to say. Here's the references. Thank you.
Thank you. I guess we can do a virtual clap. Any questions? Anybody? Oh,
Mark?
yeah, Mark had a hand up.
I'll probably ask the question that a lot of people are thinking is, you know, practical in practice. What do you think of this?
So this algorithm I presented probably will not work in practice, because what it's doing is it's essentially throwing away the linear term. I think what's probably actually happening in practice is that the noise is different from what we're doing in theory. So we're doing this very weird diagonal noise, which basically causes the linear term to be 0. In fact, you can also prove something if you were just adding Gaussian noise or mini batch noise. What it will do it'll make the kernel only learn linear functions. So instead of just linear in the feature space, it'll just learn linear functions. And then after that, it has to go away. The problem in theory is that after it goes away, we don't know what happens. But in practice, that's likely what it's happening, is that we've done some experiments, and then what we see is that it learns the best linear function, and then after that, we don't know what happens. Like, it's learning something, and whatever it's learning is pretty good, but we don't know how to characterize it. So what I've done here is something very brute force, is I've just completely deleted the linear term, so then I know what happens.
Could you just do the NTK and then add this second order correction to it? Is that something?
Yeah, my co-author has experiments on this, and he shows that he shows something like, so NTK and a neural net, you know, they differ in test error by a huge amount, 15% usually. And he shows that if you go up to like 4th order, you can get within like 5% or something. Like, you can get better and better approximations. Eventually you run out of memory and things like that. But
that makes sense.
yeah, but like, you can close a considerable amount of the empirical gap by just looking at the optimization trajectory of these higher order approximations.
Another question is, I know in one part you added the weight decay, the L2 regularization.
Yeah.
Wasn't there recent work showing that like creates bad local optima?
Is there? So definitely we are not getting the, yes, okay, how to phrase this. You cannot get the global minimum of the loss plus L2 regularization. That would solve parity, I think. But what we can get is the global minima of that within a very restricted region, which can already improve the sample complexity. So what I'm saying is, if this right-hand side here were not m to the minus 0.25, it were 1, that would be computation, that would break some lower bound. But in some small region, you can still do it. But it's a small region, but it's bigger than the NTK region. The NTK region was 1 over root m instead of 1/4.
Okay, does anyone else want to raise their hand? I see I have a bunch of my students are on the participant list. Maybe everyone's shy and or Monday tired today.
Yeah.
What other things are you working on these days?
I've been looking a lot at self-supervised learning and like these various representation learning things, but especially self-supervised, like seeing why just predicting things, essentially things you already know, like blanking out a part of the image or blanking out a word, predicting that can sort of reduce sample complexity.
I see, trying to fill in the theory for why these
So these
heuristics work.
Yeah. Because I find that very surprising, somewhat surprising. That you're predicting something that's not directly related to, let's say, the label or something. Like, yeah, I guess like supervised pre-training is not that surprising, but.
Well, I kind of think of it as like a lot of the learning you do when you train a neural network is pretty similar across different tasks. And so
Right.
maybe if you can just define some task where you have a lot of data, you can save yourself a lot of the redundant learning, even if it's not quite learning the right task.
That's right, yes. Yeah, it's possible even if you did it on random labels or whatever, it could learn something good, maybe, I don't know. Yeah, so I've been looking a lot at sort of representation learning type things. And a little bit at like sort of what SGD noise does.
There's a question for one of my students in the chat saying, or can you see that yourself?
Yes. It seems that kernel methods work well for tabular data. Any theory why neural net? What is tabular data?
I'm guessing it means discrete, like in when you fit the CPD of a Bayes net.
The CPD of a Bayes net.
So you're just fitting a general discrete distribution. Mapping from 0, 1 to the D to 0, 1 or something like that.
I see. But that would be just counting, right? There's no fitting there, I think. Yeah, I mean, there's sort of just counting, right?
You need some sort of assumption or like conditional dependence or low rank structure like that. Otherwise, it's basically you can't really do it.
Yeah, I see. I honestly don't know.
I guess there's things like restricted Boltzmann machines and so on that have been used to try and.
Oh, I see. This is like structure learning of graphical modelers.
Maybe.
Like, yeah, like both RBM. Okay. Yeah, I don't know.
Okay, well, if other people don't want to step up, maybe I'll step out and give it back to Leon and Aaron.
Yeah, I think no one else is raising hands, so it might be just beginning of week fatigue. But last minute questions, anybody? No. Okay. All right, then I think we should thank Jason again, and hopefully we'll see him physically at UBC at some point once all the things that are going on are over. Yeah, thank you.
Thank you. Thanks for having me.
Thanks.
Thanks, Jason.
Thanks.